This video illustrates the problems associated with lead screw whip on CNC machines. I also suggest a practical solution. The feature is designed to be retrofitted to a Workbee CNC, but should be easily adapted to any other manufacturer or DIY build. I should point out that I do not actually own a CNC, but I have had a lot of experience with a Workbee during a modification to allow edge carving. Various items used in the build were purchased from Ooznest, but no sponsorship was involved. The problem: lead screw whip is the vibration or oscillation that happens when a long rotating lead screw bends and wobbles around its axis at high RPMs. It's common in CNC machines, 3D printers, and linear actuators that use long screws for motion. Every screw has a critical velocity or a maximum rotational speed it can handle before vibration and whipping occur. The longer and thinner the screw, the lower this critical speed will be. Some solutions: increasing the lead screw diameter will increase the critical speed, however, the trade-off is added cost and probably an increase in motor torque to drive the axis. Changing the nut and reducing the number of starts on the lead screw will cause the axis to move a greater distance for each revolution. Slowing down the rotation speed may help with whip, but there will be a trade-off with resolution. Moving from Acme threaded rods to ball screws. Pre-tensioning the screw will help raise the critical speed but may increase wear and friction. In this example, the spring washer provides the necessary tension and the shaft collar retains it. Another solution would be to anchor the screw shaft and rotate the nut. This is common on larger machines, but increases complexity and costs. This was a prototype I built many years ago to trim ACP panels. I designed this device to provide additional support for the lead screw, effectively splitting it into shorter sections that would not be affected by critical speed. The central part simulates the gantry and is connected to the lead screw with a brass nut. The two steadies are free to move and locate in upper and lower extrusion slots. If the steadies were left to their own devices, they would be pushed to each end of the extrusion, leaving sufficient unsupported shaft, which defeats the object and cause whip to occur. I added a magnetic latching system that enabled the gantry plate to move the steadies into the correct position. Two extrusion nuts are positioned so that the steady will trip the gantry release and leave the steady in place. The gantry will then continue to its next position. This will happen at both ends. Detail of a steady, opposite end is a mirror image. The base is a phosphor bronze bush cut in half. This locates in the two carriers that can be positioned under the screw shaft without having to dismantle the axis. The lower bush carrier is secured to the top with 4 screws. At each end of the steady are the trip levers. These are held in place using magnets to ensure they cannot over-rotate and prevent gantry movement. The gantry plate has 2 flaps that can latch onto the steadies. Magnets hold these in the open position, but as the flap passes over the steady, more powerful magnets pull it down to latch. Operation of the first prototype. Note the 2 trip nuts can be placed at any position, which allows fine-tuning. This test extrusion is only 500 mm, so we will never see any whip with the 3 items on the lead screw. The latch mechanism can cope with high and really low speeds and will always latch and release. The belt drive is a 2-to-1 ratio to get higher travel speed for the tests. All the components were transferred to a 1.5 meter extrusion to see how this performs. The whip is very obvious. The steadies are positioned for easy initial latching by the gantry plate. You will note a small amount of whip as the gantry moves to collect the right-hand steady. This would probably be removed with fine-tuning the steady's position. There were a few problems with this design. Sometimes there would be too much friction in the slides and the motor would miss steps. The gantry plate needed to be a proper representation of the Workbee system to prove it could be installed without dismantling. I also needed to find a better solution for the steadies to provide a more rigid fixing. This would prevent any unnecessary radial movement and contain any possibility of whip occurring. This design uses a clip-on carrier for the latch plate and small V-slot wheeled plates to hold the new bush assembly. Operation and principle still the same, but a much more stable solution. The latch carrier plate is a simple design that makes use of the large hole in the center of the gantry plate. There are just 3 components: carrier, hole clamp, end clamp. The hole clamp screws to the carrier. Carrier slides onto gantry plate. Carrier is secured using the end clamp which fits between the gantry plate and nut block. The new slider wheels run in the top rear grooves and is coupled to the new bush carrier and trigger mechanism. The slider assembly sits very close to the gantry plate during movement, so the loss of travel is around 100 mm over the full axis. Both ends of the lead screw are fitted with thrust bearings to handle the added tension and reduce wear. I incorporated a timing system to monitor gantry speed using a modified stopwatch. The steady runs a lot smoother. This is before the steadies have been positioned. Whip is clearly present. The steadies were initially positioned to split the shaft into 3 sections. The optimal position for each steady is at the halfway point on the longest unsupported length on either side. In this case, it is about 650 mm in from the shaft end. The new positions remove any whip. I think this has demonstrated that the principle is sound and could be of use if higher transit speed is needed. The only negative is losing 100 mm of travel on the axis, but again that may not be a real problem unless you need the full travel. This has been demonstrated on a 1500 mm axis, but I see no reason why it would not work on much longer lengths with the addition of another pair of steadies. It would be a fairly simple task to equip the steady with a suitable flap system to collect and release another steady. There are probably many design changes that would improve the system, so I am not going to take this project any further. I hope you found it interesting. Apologies for the AI voice, it was meant to be my own but not in the best of health at the moment. Please feel free to leave any comments on the YouTube page. Edited in DaVinci Studio. All video copyright Pat Cooper 2015.